Hello YouTubers, it is of course me, Trollface the Man, and welcome back to another Patreon early release video. This is a series of videos I release to my Patrons a few days before their public release. If you want to become my Patreon and help support new videos by buying project materials and just in general, then please check out my Patreon link in the description below, and like I said, you'll get early access to videos like these. Today we're going to be doing something that may seem a little bit pointless, but I thought could be a fun little project for us to play around with. What it is I am going to fix the horrible quality of these LED nightlight bulbs. So long story short, I have a nightlight fixture here. It's just a standard wall plug, American, so 115, 120 volts. And I have a LED bulb that's meant to go in there. Construction of this nightlight seems pretty simple. It appears just to be a photosensitive resistor in here, or light detector. It probably goes to some type of transistor or power relay, and basically when there is no light getting to it, it allows the transistor to open and let current go through, lighting up the bulb. And when it's not open, it actually should be, with a regular incandescent bulb, it should be completely unlit, but because these LED bulbs use so little current, just the amount that's leaking through right now is actually letting the bulb stay continually lit. So what happened with this is it had an incandescent bulb originally, which is one that has a filament in it, just a standard incandescent bulb. The incandescent bulb that was in there ended up burning out, so I needed to buy a new set of bulbs, or a new bulb just in general. Well, to buy a 4-pack of these incandescent bulbs cost about $3. To buy a 2-pack of these LED bulbs cost about $3. The thing is that this LED bulb right here actually has a few more lumens than this incandescent bulb, and it uses 0.7 watts versus 7 watts. So it literally uses 1/10 the power. Now, don't get me wrong, you're not going to really see any savings on your power bill using a 0.7 watt bulb instead of a 7 watt bulb, because the amount of power they consume is so unbelievably small, you won't see a difference. But it is cool that it's using less power. If you had maybe 20 of these things in your house, then you might see a very, very marginal difference. But the main thing is that one of these LED bulbs for this nightlight should theoretically last, I don't know, 5 years. While one of these incandescent lights will probably last you about a half a year. So just having one of these bulbs instead of 4 of these bulbs, you're saving a ton of money because you're overall paying less to replace the bulbs over and over again, if these bulbs actually last the amount that they're supposed to. Now, the issue with these LED bulbs, or these specific ones that I end up getting, is that, well, they're kind of crap, and I will show you why. If I turn off my lights here, so it's going to get a little bit dark, or a lot dark, but if I cover this photosensitive resistor, you can see that the LED light lights, which is what we'd expect. But watch what happens if it's a little bit away. Yeah, this thing strobes like crazy, and what's happening is my hand's blocking the light, so there's too little light, which is causing this to trigger and to push current into this bulb. What happens though is when the bulb lights up, it reflects off of my hand. Try and get this back in focus again. It lights up, it bounces off my hand, which causes this sensor to detect that there's light, which means it stops the current, which means the light turns off, which means that it's no longer getting enough light, which means that it causes it to trigger again and turn back on. So it's a very vicious cycle. The other thing is that if we have this light lit, I don't know how well you can see it on camera, but if I'm waving my hand back and forth in person, it looks stuttery. It's like kind of like this while I'm moving. And that's because this light does not have any type of smoothing to it. So what's happening is it's like flickering at like the 60 hertz that it's coming out of the wall. From what I can see is it looks like it's specifically a full wave rectifier than maybe a resistor in there. So like I said, it's no smoothing capacitor, it's just 60 hertz flickering. Now this isn't such a big deal when you take a incandescent light, filament based light, because if I do this again, I put this light in, you can see it doesn't light at all, and then if I cover the sensor, it lights up. But the main reason why it doesn't matter for these incandescent-based lights is the filament inside of them takes a second to light up and then cool off. So if you see me turning it on and off, it will sort of fade in and out. So even if we have an issue of it being like a little bit too close, so it's kind of causing it to flicker on and off, instead of being like bright flashes like the LED, where it's flashing on and off, it's more of a slight shimmer, and it finds a median point. So based on how close you are, it will adjust its brightness accordingly. And like I said, it does that instead of like the horrible flicker that you get with the LED. So turning these lights back on. So the biggest way, and also too, the other thing is that if you like move your hand around, because once again, the filament is heating up, it's glowing red hot, instead of instantaneously flashing on and off 60 times a second like the LED bulb is, you're not getting that sort of like shimmering or jumping effect. So the way to fix this was originally I was going to take a smoothing capacitor and put it inside of this this light fixture, but I didn't realize that this actually puts out a full 120 volts AC. I thought that these step down the voltage and that these bulbs are like 12 volts, but no, actually these bulbs are 120 volts. I never really had night lights before, so I had no idea that, like I said, this is putting out a full 120 volts. Because it's also AC, I couldn't, even if I wanted to, just shove a capacitor across the leads or take it apart and put a capacitor inside, because the capacitor would do nothing to smooth AC. It has to be used on DC, especially seeing as I'm using an electrolytic capacitor, which that'd be not very good. So I actually have to modify these bulbs directly, which is kind of hard because they are sealed in glass. Now at first I thought this was plastic, and I tried to like kind of cut through it using an X-Acto knife, but I found out, even though it sounds like plastic, I mean, listen to that. It sounds like plastic, it is glass. So what I actually had to do is I had to take a file for this one, I etched it around the base, and then I kind of just tapped it, and it broke off, so I was able to access the bulb's internals. The original thing is if it was plastic, I was going to cut off the bulb and then re-glue it back on afterwards, but I wasn't able to do that because, like I said, it is, in fact, glass. When I prodded, there is a pretty simple setup to this. There is a positive on this side, and then there is a negative on this side, and the base of this 1, 2, 3, 4, 5 cluster of LEDs on this sort of square structure. And like I said, I can see what looks to be a full wave rectifier, and then possibly some resistors down there. I don't want to tear it out because I'll destroy the bulb. When I measured the voltage for this positive and negative, it was about 35 through 37 volts. Now, the thing is I'm not quite sure how they get the voltage. I don't know if they use just a simple resistive dropper in here, because like I said, I can't really see much else except for what appears to be some diodes and then some resistors. So there's a theory that, you know, this positive and negative might only be about the 35 to 37 volts because it's passing through much more current, but these LEDs are in series and that it's stepping down the current. However, that's not the case because I could reverse push through 35 volts and get these to light up their full brightness. So it's not a case of these being in series. All these LEDs seem to be in parallel. So unless the LEDs in this specific chip are in series, so they might have, I don't know how many LEDs in there, but each specific chip might have, let's say, 10 LEDs in series or something. But these individual chip clusters are definitely parallel. They're not series. So this can run if I just push 35 volts back through it, which is very good because I need to use an electrolytic capacitor, and the only one that I can find that's reasonable size has to be a lower voltage of around 50 volts. So if I had to do like 120 volts, for example, trying to find a reasonably sized, a reasonable capacity and volume-wise electrolytic capacitor would have been very, very difficult, if not impossible. So I'm glad that it's a low voltage. Plus it means it's much safer because I'm not going to be able to put a glass globe back on here because, like I said, the old one was busted off. So I'd much rather have it be a lower voltage, so if you ever touch this open part, you're not getting, well, electrocuted. So let's zoom in here a bit. So to try and fix the whole quick flashing, and then also fix the shimmering that it does, I want to add a smoothing capacitor. This is going to be a very simple concept, and I can demonstrate this right now by simply taking, I solder this wire on, if you couldn't already tell. So I'm going to take this LED and I'm actually going to screw it into this fixture here. So this is going to mean when I plug this back in, it's going to be live. I have to be very careful not to break it. Okay, so it's working. If I connect, this is the negative here. So if I connect the negative to the negative of this board, and don't worry, this is going to make a lot more sense. It should actually be over here. So if I connect the negative to the negative of this board, and then I connect the positive to the positive of this light, what should be happening is we should now be getting current flowing through this board if there was any components that allowed current to flow through. Currently there are no components to do that. The other thing I want to do is I want to hook up a power meter so that way we can see what's going on voltage wise. So take this power meter and I am going to have this connection right here going to the positive, and then this one going to the negative. And I know this looks just like a giant cluster of wires. I will clarify stuff here in a second. And then if I turn this on to DC, we should hopefully be seeing voltage coming through here. Okay, why is there no voltage? Is there a bad connection here? Positive. Ah, I figured it out. It is a combination of me being really, really dumb and me being idiotic. Basically, I had a positive where a ground was, or the negative, and then I also failed to jump this over, or I messed it up after I was playing with it. I'm not quite 100% sure. But light dim, we're getting about 32 volts. 33 volts, light bright, we're getting about 34 volts. So we can now see this visualized via this power meter. And to really kind of simplify things, this is the basic circuit right now. Oh, I might have to change the exposure a little bit. Okay, so what we can see is, just completely disregard this. It's basically, we have 120 volts coming into the bottom of this bulb. It's going through something inside of the bulb, some type of circuit, full wave rectifier, and then possibly a resistive dropper, and we get 35 volts approximately rectified DC. So instead of being up and down like AC is, we get pulses. So doop, 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 doop. And that's what kind of causes the stuttering, because we're getting points at where it's 100% 35 volts and then 0, 100% 35 volts and then 0, and this causes it to flicker on and off, like I said, 60 times a second, in accordance with standard AC, American AC, which is 60 hertz. We have disconnected to the voltmeter, which is registering the 35 volts DC. What we want to do is we want to stop the sort of flickering. If you get partial light exposure, like we were showing before, it kind of flickers on and off really rapidly like that. And we also want to stop it from kind of having that shimmering effect at 60 times a second. And the easiest way to do this is to add a capacitor. Particularly, we're going to be using an electrolytic capacitor, and what this is going to do is this is going to act as a sort of battery that's going to not only make these pulsations look more like this, where it never actually reaches a 0 point, so it never actually completely turns off, which is going to give more of a shimmering effect instead of like a quick flashing effect that we're getting, but it's also going to sort of make it where instead of this turning on and off instantaneously when it's kind of getting just barely exposed, like this, we're going to add it, the capacitor is going to act more as a buffer for that and kind of create almost the effect of the incandescent, where it will brighten and then fade, brighten and fade. So to do this real quick, I already have the board set up here. And we're going to expand on the circuit just a little bit here in a minute, but I have right here a 50 volt, 100 microfarad capacitor. So to make this work, all I'm going to do, and like I said, I already have this set up, is I am going to connect this capacitor across the positive and the negative of this light, which I have a spot right here. I can do this. Just make sure the polarities are lined up. Positive and negative. That is correct. And what will happen is you can see, oh shoot, the light goes out. But worry not, because if you're looking at this, it's actually charging up. What's happening right now is this capacitor is sucking up all of the current that was normally used to light up this LED, and it's using that to charge. We can cause it to charge quicker by covering the cell, which pushes more current through. And now you can see that the light functions perfectly normal. But you might also notice that instead of turning on and off instantaneously like it was before, it's kind of fading in and out. So to give an example of what it would look like without this, I'm going to disconnect this wire, and you can see that it's instant on and off. If I reconnect this wire, you can see it kind of glows brighter and then it goes dimmer, instead of, once again, instantaneous and then fading, more like an incandescent. This is very useful too, because like I said, instead of getting that sort of rapid flickering effect that we did before, if the light was within a certain proximity, you can see that even if I put my hand really close, it's not doing that. Now if I disconnect it, watch what happens. So you can see that instantly it starts doing the flickering again. Instead of, there we go, right there. I'm going to reconnect the capacitor. You can see at that same point it doesn't do that. It doesn't do it at all, really. And the best part is about this is that when it's lit now, instead of getting that sort of like stuttering effect, it'll be completely smooth, which is kind of hard to show on camera, but I can attempt it here. If I turn off these lights again, and hopefully you'll be able to see to some extent or another. But yeah, it's completely smooth. So you can see that it's very smooth. I'm going to take this off, and we'll see if you can tell the difference, how it's kind of like stuttery. Yeah, I think you can see that on the camera. So this is with the electrolytic capacitor detached, and you can see it kind of stuttering. And this is with the electrolytic capacitor attached, and you can see that the light is very, very smooth. Perfect, just what we need. But there is a few issues with this circuit. One of which is this capacitor is going to basically act as a short circuit when it's not charged, which means that it might be stressing whatever circuit is inside of this light to charge it at first, which probably isn't good. And the other thing is that if we now unplug this light, you'll see that it's actually still, if I turn these off, it still glows, and it'll do this for quite a while because this capacitor is acting as a battery, essentially. And you can see this too represented by it slowly discharging. Now I can cause it to discharge instantaneously by just shorting it like that, and then the light will go out. But that isn't ideal. You can see once again it's going to be charging up. I covered the resistor here, it charges up much quicker. This isn't ideal because, well, you probably don't want the thing glowing for half an hour after you unplug it. So there's a few modifications I'd like to make to the circuit, which I have right here. And I'm going to have to change the exposure again. Wrong way. Basically, what I'm going to do is between the positive going to the capacitors, I want to add a resistor. This specifically is going to be a 10 ohm resistor. And what this is going to do is it's going to stop these resistors from acting as a basic short circuit. And I probably could go much lower value, maybe 1 ohm or something like that. But instead of these acting basically as a short circuit, it's going to make it where this doesn't push all of its current right into these capacitors right away. Instead, it kind of trickle charges them, which is going to be less strenuous on whatever circuit converts it to the DC, and then converts it to the about 35 or 37 volts, which might have partially to do with the LED. But actually, that doesn't make much sense. Well, anyways, the other thing I want to add is between the capacitors. So across the positive and negative of the capacitors, I'm going to add a discharge resistor. And you've seen when we pulled off the LED light off the plug, it will glow for quite a while, and that's because the capacitors are acting as a battery, essentially. So this discharge resistor is going to just let a small amount of current trickle through and allow the capacitors to slowly discharge themselves over time, instead of just discharging through the small amount of current that they're putting through the LED, which when they drop below the LED's forward voltage, they might stay charged for a very, very long time. So this is going to be a 100K ohm resistor. And like I said, it's just going to slowly let it discharge. And yes, while this is running, that means that there's always going to be a slight amount of current leaking through this resistor, which is going to waste power. But like I said, it's just a sort of luxury feature to allow this light to turn off by itself quicker. We still have the multimeter connected. And for this, just for fun right now, I'm going to instead swap my 50 volt 100 microfarad capacitor with two 50 volt 330 microfarad capacitors. So that's going to give us a total of 660 microfarads. But because we're not charging it to full capacitance, the total amount that it can hold is going to be different. We're only charging it to about 35 to 37 volts. So, turn this back up again. So right now, I'm going to take this 50 volt 100 microfarad capacitor, and I am just going to add these two 330 microfarad capacitors. Making sure to get the polarity right. And you're going to see that it's going to charge much, much slower. If I cover this, It's going to increase the charging rate. And like I said, this is probably bad for the circuit that's inside of there. And you can see that it has a very, very slow build up and then fade off when you put your fingers over the sensor. So instead of, like I said, once again being instantaneous, so if I take this off, you can see instantaneous on and off. If I put this back on, you can see very slow build up and then very slow drop off. And this smooths the light coming out of the LED even more. But even with that 100 microfarad capacitor, it's smooth so much you're probably not going to really see any type of difference. So if we do that thing again where we kind of let the light that's produced by the LED trigger this sensor to turn off, which was causing extreme flickering before, if we do that now, I'm going to turn off these two lights. So if we do that now, you can see it doesn't have that rapid flashing effect at all. To demonstrate what it looks like without this, I'm going to take it off, and you can see, yeah, that's capacitors back on. Nice and smooth. Capacitors off, and flickering like mad. Now the problem is that these two 330 microfarad capacitors are going to be way too bulky to use with this, and plus having the resistor, so I'm going to actually add those resistors here real quick. So this should be a 10 ohm resistor right here. So that is our one right here that's limiting the charging current, and then I already have the 100 the 100 kilo ohm, the 100,000 ohm resistor right here that I'm actually just going to plug in. And like I said, that's going to act as this discharge resistor between the two capacitors, letting them slowly discharge. You can see that adding this resistor right here, this discharge resistor, has a unintended but potentially beneficial effect that the light is no longer glowing by itself. So if we take this off, you can see that when these resistors charge up, the light will glow by itself just from this small amount of current that's leaking through in the circuit. But if I pop this back in, the discharge resistor is discharging quicker than that small leaking current, so the light actually turns completely off, which it wouldn't do before. This potentially could be beneficial if you didn't like the fact that it was always giving a soft glow instead of not completely turning off, because this actually allows it to completely turn off. You can see that it is discharging the capacitors like we want it to, and it'll discharge even quicker if I unplug it. And it'll eventually discharge capacitors to 0. Like I said before, they would have stayed charged for like pretty much ever without the discharge resistor. But you can see that if I cover the light sensor and it starts pushing current back through, large amounts of current to try and light the light back through, the discharge resistor isn't discharging quick enough to stop this light from lighting at its full brightness. So that is very good, and I could potentially increase the resistance of the discharge resistor to, like, let's say for example 200,000 ohms and limit losses even more, but probably not that necessary. So once again, 10 ohm resistor to limit the amount of current that's going into the capacitors at first, so it's not acting like a short circuit, and the 100K discharge resistor to discharge these when it's not plugged in or when there's not a large amount of current going through. This circuit right here, though, with these capacitors, is way too bulky to be implemented into this light, and these two resistors also make it, well, pretty bulky. It'd be pointless for me to take this entire board here and try and put it in this light. But the good news is that this circuit can be simplified pretty dang well. If we take the 50 volt 100 farad capacitor and we solder the 100K discharge resistor between the positive and negative leads, and then we solder a 10 ohm charge limiting resistor on one of the leads, and then we simply jump that right across the light here, then we effectively are going to take this whole circuit, except for with this instead of these two, and simplify it down into just one little tiny thing that can be soldered directly to the light. And to show an example of how that is, let's discharge this resistor, shall we? Oh, that wasn't very spectacular. To demonstrate how this will be attached is all I'm simply going to do. On the solder points of this light here, I can literally take the positive of this, solder to one side, and the negative to the other side, and you can see that it will do exactly what that entire circuit did, except for extremely simplified. Yep, see? And like I said, I'm going to solder on a resistor, a discharge resistor, and also a charging limiting resistor, and just solder right to this light. So let's do this real quick. All right, so this is the positive and negative of the 50 volt 100 microfarad capacitor. I have the 100 kilo ohm resistor, the 100,000 ohm resistor, already cut here, ready to be put on. So the first thing I'm going to do is tin the leads of this electrolytic capacitor. Okay. I am going to tin the leads of this resistor down here. It's going to be a little bit blurry because I'm not going to refocus it. The camera might refocus it, I'm not sure. Okay. So that's been tinned. I'm now going to take this resistor and dip the ends in a little bit of flux. And hopefully, if I just drop this on here, I have to expand this out a little bit. A little extra solder here. So that should be soldered to the one side. Now, going to solder this to the other side here. So it didn't take the initial time. I'm just gonna okay, I know it took that time. Yep, it's a nice big old glob there. Okay, so now what's left to do is to solder the current limiting resistor. Please ignore that. So that was my phone notification, or a notification from my phone. So this is the 10 ohm current, charging current, limiting resistor. Maybe one of these leads a little bit longer actually. The camera's view. Okay. A little bit of flux on here. Try and get it to flow. Okay, perfect. So now, this has a discharge resistor and it has the current limiting resistor for charging on it. What we're going to do now is take that bulb, unplug it. I'm going to take this bulb here. Going to desolder this wire real quick because there's no reason for that to be on there still. So I did something really stupid, and this is going to lead me to do something probably equally, if not even stupider, which is when I desoldered that wire, I forgot to mark which side was the negative and which side was the positive. So what I'm going to do is I'm actually going to hook up, hook up a bunch of 9-volt batteries together, including alkalines with super heavy-duty ones, because I am particularly bad, and use that to test to see which way, which orientation the positive and negative is on this light. So, oh, yep, I touched that to my tongue. Oh, it definitely has whew, quite a kick to it. Alright, so, okay, that looks to be it. So this top one is the negative, and the bottom one is the positive. Oh man, my tongue still hurts from that. That was, whew. How many volts is this? Oh man, I am really good at knocking stuff over, I swear. See how many volts this is. That on the old screen there. Yeah, so about 41 volts, 41 and a half volts. So, yeah. That felt great. Oops. Okay, I think the best way to solder this on is using something like this, where I kind of solder it top and bottom like this. So to do that, I'm going to do the same thing that I always do, which is tin the leads first. Okay, that has been tinned. That doesn't need to be tinned. Give it a nice dip in some flux. And then right to there. Perfect. And now I'm going to flip it around and solder this connection to the other side. Dip my solder in a bit of the flux. And, in theory, that should be good. Alright, well, if I'm not a complete idiot, then this circuit right here, minus the old power meter or power tester, and instead of having these two 330 microfarad capacitors, we only have one 100 microfarad capacitor. It should all be simplified into this little circuit here, which is this right here. So the only way to test it is to screw it in and see if it works. And if it doesn't go pop, then hopefully I would have done this right. Very careful. Okay, here's the moment of truth. Oh, phew. For a second there I was worried. Thought the old capacitor might have had the wrong orientation, in which case it would have got pretty hot pretty quick and then went boom. Seems to be working though. So, has a sort of gradual light up and then fades, and now it actually stays completely off when it doesn't have current going to it. That's a plus. And then if I have it close, like my hand close or something, we'll see, does it? It doesn't cause itself to automatically flicker on and off like crazy. Instead, it basically lights up to a brightness that finds an equilibrium. Yeah, look at that. Cool. So, I think this actually ended up working out pretty well. Let's try and see if I can find the cover for this thing now. Ah yes, I was able to find the diffusing cover. So with the diffusing cover on and looking from the front, you'd probably be none the wiser as to the electrical monstrosity going on behind the scenes. So yeah. Let's turn off these lights. As you can see, it's no longer strobing like mad. It's no longer like we are partying at a disco. It finds a brightness based on its light input. Let's try and pop this one in real quick and see what it looks like with that one instead. See that it fades off. Alright, so here is the regular unmodified bulb in here, as you can see. Yeah, and this is what I was having to deal with all the time. Yeah. So hopefully you can see that this bulb right here is quite an improvement over that. And like I said, even when it's on continually, you still get that shimmering effect, which isn't ideal. Yeah. Anyways, guys, thank you very much for watching. I hope you enjoyed this video, and if you did, please remember to drop a like, a comment, to subscribe if you haven't already, and please consider supporting me on Patreon. I always appreciate it, and like I said, it helps buy supplies for new videos. And yeah, I thank you guys very much for watching. Thank you, and please check out another video if you have the time. Goodbye.